Now, if you can see my screen.
Yeah, you can see your screen.
Okay, and I'm assuming you can hear me clearly as well. I'm going to test my annotation, and you can see my annotation, right?
Yes.
Okay. Right. Good afternoon or evening, everyone. As Philip mentioned, my name is Naser Ibrahim, and I am part of the academics in the School of Computing at the University of Buckingham. And today, we're going to look at the fundamentals, basic fundamentals of neural networks and generally advanced machine learning. So throughout the session, I'm happy to take any questions that you might have either during the session or after the session. I don't have a side of the chat, so if you have any questions, probably it would be better to just open your microphone and ask your question, or you can raise your hand and then hopefully I will get a notification and then you can ask your question, or Philip can indicate to me as well. Okay, I understand that you're preparing for a professional machine learning engineer certification, and this is part of sort of the study and to just get a study group together and go through the learning journey as well. So what are we going to cover today? So we're going to recap machine learning fundamentals, and specifically we're going to focus on one of the sort of most critical method in machine learning, which is neural networks. And we have a lot of systems that are based on that, and we'll touch on that in a moment. And we'll look at how it works at a fundamental level. And then later on, Philip is going to take you on a journey, recapping on sample questions and exercises, and we'll take Q&As after. Hopefully, we will cover as much content in the next 52 minutes. So let's start by just looking at the basic fundamentals of the difference between AI, machine learning. We have heard, I'm pretty sure everyone has heard of artificial intelligence, and now it seems like everything is being put onto or AI is being put on every system, whether it's a robotic system, whether it's a computer vision system, or whether it's a really ChatGPT, for example. Everything has a label of artificial intelligence. But actually, artificial intelligence is a very broad term, or it's an umbrella term that includes so many things in it. Basically, anything that relates to computer mimicking human intelligence is considered artificial intelligence or application of artificial intelligence. That could be robotics, that could be self-driving cars, that could be document categorization system, that could be a diagnosis system. Okay, everything has the label of AI. But inside of that AI, we have what is called machine learning. Okay, and machine learning is a subset of artificial intelligence. And what it allows to do is for computers to learn without explicitly being programmed. So you don't have to write sort of instructions to carry out a task. What you need to do, or what you do, is you train a system, you provide it with a lot of data, and then it learns to map either input to output, or it learns to understand the features or the relationship between the data. And inside of machine learning, we have different subsets of machine learning. So we have supervised learning, we have unsupervised learning, and in the intersection of that, we have deep learning as well. Okay, so these are subcategories of deep learning. And we have actually a third category, which is called a semi-supervised learning as well. And some of you might be familiar with another type of learning, which is called reinforcement learning as well. But we are not going to touch on that today. But in this session, we're mainly going to focus on deep learning. But before that, let's see sort of an exploration of what supervised learning is, what unsupervised learning is. So, like I said, there are two main types of machine learning, supervised learning and unsupervised learning. Let's take supervised learning. What is supervised learning and what does it do? Now, supervised learning, this is where you have sample data, or you train a model with sample data, and you know the answer to the sample data, or you know the identity, or you know the label of the sample data. For example, if you have a task where you want to classify, in this example, classify an image. Okay, so you have images of different animals and you want to classify them. Okay, because for each image, you know what animal is in there. So you know that this image is an image of a dog. This image is an image of a cat. So what you do is you build a model that will take in that image and will be able to tell whether that image is of a dog or that image is of a cat. Okay, and that is with a label data, because you know the label of each image. Okay, you know the label of each image, so you can train a model to map the characteristic of the image to that particular label. And then once you train that model, you can give it a new image, and then it will tell you whether that image is an image of a dog or an image of a cat. Another example is spam detector, for example, for an email. When you receive an email, you might get a tag saying, okay, this email might be a spam email or might not be a spam email. Okay, that is because the model has been trained to identify and to differentiate between spam and not spam emails. Okay, so when you have a data and you have the label of the data, that is considered to be a supervised learning problem, and you have supervised learning algorithms that you build. On the other hand, you might have a set of data that actually you don't have a label for them. Okay, you don't have a label for them, but you still want to classify them, or you still want to differentiate them, or you still want to segment them. So what you do is you build an unsupervised learning model. And an unsupervised problem is a problem where you have a bunch of samples, but you don't have a particular label for each sample. Okay? And in this case, it could be a bunch of images, but you don't have the tag of the images, whether they are images of dog or images of a cat. Okay? So in this case, the unsupervised learning is going to go through that data and is going to look at several features, and then it will segment the features that are close related together. So in the end, you might get a cluster, and one cluster would be the samples that have features that are very close, and then another cluster would be of features or samples that are very close. And if we go back to the example of the cat and the dog, you would have dogs will have similar features, cats will have similar features. So an unsupervised machine learning model will learn the characteristics and will be able to differentiate between those two. So if you have the easiest way of differentiating supervised or unsupervised learning problem is just look at your data. Do you have label? If you have a label, then that is a supervised problem. If you don't have a label, then that will be an unsupervised learning problem. And there are different techniques for each of them. And of course, the way of evaluating the models are different as well. Now, let's go a bit deeper and look at the different types of supervised learning. There are mainly two that, at least for now, you need to understand. We have classification and we have regression. So let's say, for example, you want to predict a cat or a dog. you have only two classes there. Okay, and because you have only two category of classes or discrete classes, then that is considered a classification problem. So a classification problem.
Very nice, sir.
Yes.
Yeah, I'm sorry to cut it short. I think we've actually explained this early part, so if you can, you can just brush it, yeah, and then dive into the yeah.
Okay. I did not know that. Okay, so very briefly, classification problem, you have discrete classes. Okay, you determine whether a picture is of a dog or a cat. An example algorithm is logistic regression. Then we have another class of problem, which is a regression. Now, this is where you predict numeric data or numeric variable. For example, you want to predict the price of a house. Price of a house is numeric, it is continuous variable, right? So in that case, you're predicting a number, and that will be considered a regression problem. An example of that is linear regression. Okay, so these are the two main classes of problems under supervised learning. And then for unsupervised learning, different, again, classes of problems. We have clustering or segmentation, which the example that I gave earlier, when you don't have labels of an image, it groups them based on the related features. And one example of a clustering model is K-means clustering. And then you have another class of problem, which is association, which identifies the relationship between different attributes. And then you have dimensionality reduction, and this is a class of unsupervised learning where it reduces the number of dimensions. So you might have a case where you have a data set with so many features, maybe hundreds of features, and it will be quite computationally complex to build a model with that number of high cardinality of features. So what you do is you apply a dimensionality reduction technique, which is going to reduce the dimension of the features or the cardinality of the features to the most important ones. So you can train a model and get a good performance. And one of the approaches is called principal component analysis. Okay, so with that being said, and with that understood, now let's look at neural networks. So neural networks, with the example of the cat and the dog, for example, you can have different algorithms. And one of the algorithms that you can apply is a neural network. Now, neural network is the foundation of LLMs now that we have, or convolution neural networks that we have now, or the current neural networks that we have now. And we're going to look at, we're going to lift the hood slightly to understand how the neural network works, okay? And so we're going to focus on artificial neural network to understand the fundamentals. But the concept is applied to other types of deep learning, and basically it's a more sort of expanded version or exploded version of the artificial neural network. Now, if we look at the structure of a neural network, an artificial neural network has three layers that we need to understand, and these are the fundamental layers. So we have the input layer, we have the output layer, and in between that, we have the hidden layers, okay? Now, we can have one hidden layer, we can have any number of hidden layers. That's actually a parameter that you define when you're developing the model. And depending on the number of hidden layers that you have, it might be considered a deep neural network. And what do you do in the layers? That's the main differentiation between the different types of neural network. Now, in addition to that, in each layer, you have what are called neurons, okay? You have neurons. So in the input layer, for example, we have 3 in this case. in the output layer, we have 3 as well. And in the hidden layer, we have 5 layers as well. Okay. So we have input layer, we have output layer, and then we have the hidden layers. Now, between each of the neurons, there is an interaction, or there is a information that is transmitted between them. And you can see that with the lines, there is a connection between each neuron to every other neuron. Okay. Now, how can this be applied on a basic level when you have a data set? Let's say, for example, we have articles on the left here. So these are our sample data. And we want to see what article, okay, or what outlet published this article. So what we want to do is we want to pass this article to the input layer, and the output layer is going to tell us, is it from GitHub, is it New York Times, or is it TechCrunch? Okay, and so this input will be transformed, the samples will be transformed into the input layer, and then some computations will be done. And at the end, we're going to have an output to tell us, okay, this particular article is coming from GitHub or New York Times or TechCrunch. Okay. Before we continue, what type of problem is this? Can anyone tell me what type of problem this is? Is it a okay, on the first level, is it a supervised learning problem or an unsupervised learning problem?
Unsupervised.
Unsupervised. Why do you say unsupervised?
Not similar data. GitHub, New York Times, TechCrunch. Not labeled, not in the same category.
Not in the same category. Okay. Any other one? Any other views? I see Alex. Alex is saying unsupervised as well. Well, Alex is not sure whether it's a classification or unsupervised. Okay. Now, if you have a model like this, and it gives you this output, in order for the model to be able to map the input to a class of the output, it must be trained with a sample data. And that sample data, you have the articles, you have the publication that the articles are coming from. So you know, okay, you know, and then you train the model. And if you remember, the difference between the supervised and unsupervised is that for supervised, you know what the labels are. For unsupervised, you don't know what the labels are. So in this case, because the label tells us what particular publication an article is coming from, then this is a supervised problem because we already know the label. Okay, so this is supervised. If you didn't know the label, basically you are training the model to segment. Okay, these articles are related together. These articles are related together. These articles are related together. If it gives you that segment or that clusters, then that is unsupervised. If the output is segments, that's supervised. But if the output is a label or is a number, then that is a supervised problem or supervised learning. That's on the first level. On the second level, so if we know it is a supervised problem, what type of supervised learning problem is this? Would you say it is a regression or classification problem? So this
I think it should be.
Say that again.
I think it's a classification problem.
You think it is a classification problem. Why do you think it is a classification problem?
Because based on this set of outputs and set of data we are being given, we are classifying them into GitHub, New York Times, and TechCrunch. So we are basically classifying them.
right? So we have a specific categories that the articles are mapped to. And yes, that is a classification problem. Okay. If let's say it was a numeric output, okay, then that will be a regression problem. Okay, let me ask you another question. What if we have, so classification problem, I'm not sure if it was explained to you earlier, but a classification problem could be you have only two outcomes, or you can have more than two outcomes. So if you have only two outcomes of a classification problem, so for example, classify a dog and a cat, that is considered to be a binary classification problem. Okay. If you have more than two classes, it is considered to be a multi-class classification problem. Now there is another type or a class of classification problem which is called a multi-label, which means that you can have a sample that maps to more than one class. But that's more advanced. But what you need to understand is for classification, you can have two output, which is called binary classification. You can have more than two outputs, which is a multi-class classification problem. Okay, so let's go and see how a neural network works. How do we map the input to the hidden layer and to the output and get a label at the end? Okay. I'm going to take you back to elementary school in a moment, primary school, with a bit of mathematics. Now, let's assume that you have two input neurons. Okay, so you have two input neurons and you have one hidden neuron, and then you have one output neuron as well. Now, the connection between each neuron, so there is a weight that is attached to that. So every link has a weight attached to it. Okay, so these are input. Let's say the input are A and B. So there's a linear relationship between the input and the hidden layer, and between the hidden layer and the output. Okay, and these weights are learned during the training process. Okay, so when you are training the model, one of the things that the model learns is this weight. And depending on the values of weight, the performances of your model is going to change. Okay, the performances of the model is going to change. And to give you an idea of the size of LLMs and all of those sort of large models, you have models now that have this number of weights in the billions. So you might have 7 billion or 1.3 billion and so weights. Okay. It's a double-edged sword because yes, if you have that number of weight, it means that you're going to have a very large network, which means that you're likely going to get a very high performance. But then on the other hand, explainability is a problem, which is another set of problem with neural networks. Okay. Anyway, so here, what we need to understand is between each neuron, there is a connection, and the weight retain the information that the neural network learns through the training process. And this actually, well, someone said these are the mysteries of neural network. Okay, the mysteries of neural network. So at the very basic level, you know that we have the input, we have the weight, and there is a connection between the neurons in the different layers. Now let's see how they work. So the first step, imagine we have the input x1 and x2. Okay. Now, in order to map that to the hidden neuron, actually what is done here is a weighted sum is calculated. Okay, a weighted sum is calculated, and that weighted sum basically is the value of the input is multiplied by the value of the weight. Okay, the value of the input is multiplied by the value of the weight, and then that is summed up, and that will give you the value of the hidden neuron. Okay, so in this case, it will simply be x1 times w1 plus x2 times w2. And that will give you the value of the neuron here. Okay, so it is the weighted sum of the product of the input as well as the weight. Okay, so you multiply the input value by the corresponding weight, and the sum of that will give you the value of the neuron. And actually, there is another term that is added, and this term is called the bias. So usually the equation, you have a bias term that you add to it. Okay, and for the moment, we're going to ignore that bias term. Like I said, I'm going to take you back to elementary school. Does this equation remind you of a particular maths concept? Yes. Alex said y equals mx plus b.
Almighty formula.
The almighty formula. Well, the almighty formula is plus minus the quadratic equation. That's the quadratic equation. But yeah, this is the equation of a linear relationship between attributes, right? So you have two attributes, x and y, the equation of a line. Okay, yeah, the equation of a straight line, absolutely. What is x? What is m? Anyone remember?
I think it's the equation of the slope.
Yes, that is the slope. Okay, m is the slope. Okay, how about b or c in this case?
Is the intercept.
That is the intercept. So the line that it crosses the y-axis, right? So that's the intercept. Yeah. So actually, what is going on inside of a neural network is simply a linear equation. Okay, so mx plus b. So x here is the feature. Okay, x here is the feature, and m is actually the weight. So for each x term, you're going to have a corresponding weight for it. Okay, and that would give you the value of the hidden layer. And actually, that continues to happen for all of the layers that you have. If you have neurons, all of the layers in the neuron, that's how the computation will be done. So if we have, let's say we have another neuron here, so it will be the same thing. So we'll have weight here, W3, W4, and the same thing will be here. Okay, and for each hidden layer, that is what will happen as well. Okay, that's what would happen as well. So underneath, that is simply the computation that is done. Okay. Now, that is the first step. So the first step is the computation of that, the computation that is done. The second step is applying what is called an activation function. Okay, an activation function basically, so the value that you compute, you apply an activation function. And in a moment, I'll go through some examples and also tell you what an activation function is. Okay. Okay. So at each neuron, you apply an activation function, and then based on that activation function, you get a new value on the neuron. And again, the value will be computed with the weight, and the output layer will be determined as well. And again, the same linear equation will be applied there. Okay, so this computation continues to happen until you have all of the neurons and all of the outputs as well. Okay. Now, the activation function is applied both on the hidden layer as well as on the output layer. Okay. Both on the input layer and the output layer. And again, it is the weighted sum. And the activation function can be different to the one applied. So you can apply a different activation function on the hidden layer, and you can apply a different one on the output layer, depending on what you want. Okay. And When you apply the activation function on the output layer, you're going to get a value. And this value is going to be what is called your predicted output. Okay. And once you have the predicted output, okay, from the output layer, you can compare it with the actual output. Okay. If you compare it with the actual output, that will give you an indication of the performance. So let's say, for example, you are you want to classify an image into cat or dog. Okay, all of this process will be done, and at the end, the output layer will tell you, the output will tell you whether this image is of a cat or this image is of a dog. But because you know the label, you can compare and see, okay, I know this image is of a cat. The model is telling me that this image is of a cat. Then that means the model predicted correctly. I know that this image is of a dog, and the model is telling me that this image is of a cat. That is incorrect. So the model is incorrect. Okay, so this is a way that you can evaluate the performance of your model based on what it outputs, the predicted output, as well as the actual output. And later on, Philip will explain to you some of the metrics that you can derive for the performance. Okay, so that is the fourth step that is done, determine the output based on the activation function that you apply on the output layer. Now let's go back and see what an activation function do. Basically, in short, an activation function is used to prevent linearity. So if we go back to the equation, we know that in order to determine the value of the hidden layer, it's basically a linear equation that we apply. Okay, and if we take that value, let's say the value of h, okay, the value of the hidden neuron in the hidden layer, and again we do the computation, we multiply it by the weight, we are going to get an output layer. But now the question is, if we simply go leave it in terms of the linear equation, apply only the linear equation in the hidden layer and on the output layer, why not simply apply the input, simply get a weight that would determine the output for you? Because it is a linear equation. Actually, to further emphasize that point, if we want to determine y, if it is a linear equation, you basically need to do this. So basically this term, all you need to do is to add h w3. So to add this weight, multiply by these values. Right? So then you don't need this actually. You don't need this actually. Okay. So the activation function actually prevents this linearity. Okay, it prevents this linearity. Okay, and that's what I explained. Okay, it prevents this linearity. Otherwise, we could just take the input, multiply that by a particular weight, and determine the output. Okay, so these are some examples of activation function. So activation function basically determine what neurons fire, what neurons do not, and also what influence each neuron should have. Okay. And there are multiple types of activation functions. The first one is called rectified linear unit. Basically, what that happens is, dependent on the value of the computation, the activation function will bind it to values between 0 and 1. Okay, so if you have a negative value, the negative value will be capped at 0. Okay, and the positive value will be capped at 1. So you would have values between 0 and 1. Okay, so that is the rectified linear unit. The second one is a sigmoid function. Okay, the sigmoid function is also a function which turns the input to a value between 0 and 1. Okay, so it turns a value between 0 and 1. So if you have a negative value, it will be capped at 0, and then the positive value will be capped at 1 as well. Okay, actually the rectified linear layer, it caps the bottom, which is 0. Any negative value would be 0, and then the positive value will be kept as it is. But the sigmoid function caps at 1. Okay, so it scales the values between 0 and 1. And then finally, we have the hyperbolic tangent, which basically caps between -1 and 1. Okay, -1 and 1. Okay, so if you have, based on the value of the weighted sum that you calculate, depending on the value, you can, and depending on the activation function that is applied, you can either map it into a particular range, depending on the activation function that I used, and dependent on the problem that you have as well. Okay, now why do I say dependent on the problem? Because if you have a binary classification problem, for example, you have to classify an email into spam and not spam, you have two classes. Okay, the activation function that you use will have to be different to the activation that you use on the output layer when you have more than two classes. Okay, now the sigmoid, if I go back to the sigmoid, it gives you a value between 0 and 1. It gives you a value between 0 and 1. Okay, now if it gives you a value between 0 and 1, basically you can map the labels of the output to that particular window. Okay, so it can tell you, if you have an email, it can tell you what is the probability of the email being spam or the email being not spam, and that will be a value between 0 and 1. Okay, if it gives you one value, you can of course derive the other value, which is just 1 minus that value. But when you have more than 3 classes, okay, or more than 2 classes, which is a multi-class classification, in that case, you are not necessarily going to apply the sigmoid. Okay, you're going to apply another one, which is called a softmax. Okay, the softmax, think of the sigmoid, but it generates a value between 0 and 1. Okay, but for multiple classes. Okay, for multiple classes. Okay, an example of that is here. So the output of the submax is a probability distribution. Basically, what does that mean? It means that the outputs that you get, if you sum all of their probabilities, it's going to amount to what? Okay, even sigmoid, of course, if you sum the two probabilities, it should give you 1. So the output, when you apply the output, it's going to give you the probability of the output. The probability of the output. So for example, in this case, if you give it a sample, it might tell you the probability of this article being GitHub is, let's say, 0.6, and New York would be 0.3, for example, and TechCrunch would be 0.1. If you sum these probabilities, it's going to amount to 1. Now, when you come to determining the label, how are you going to determine the label if you have these probabilities? What do you think? How are you going to determine this label?
Or it should be higher probability.
You take the one with the highest probability, right? The one with the highest probability that will map to GitHub. So your output label is going to be GitHub. Okay. Okay. So that is softmax. So now if I go back to this, the softmax is actually sigmoid, but for more than 2 classes. Okay, it's sigmoid for more than 2 classes. And actually all of these activation functions, you can apply them in the hidden layers, or you can apply them on the the output layer. But you have to be careful and you have to understand the type of problem that you're looking at. So if you have a binary classification problem, you can apply Sigmoid. But if you have a multi-class classification problem, you cannot apply Sigmoid. In that case, Softmax would be the most appropriate. Okay, and what you need to understand is the softmax is a probability distribution function. Okay, so again, a more differentiation. Softmax is applied to multi-class classification problems, and the Sigmoid is applied to binary classification problems. Okay, so the application of that, the activation functions, you don't have to, like I said, you don't have to have the same activation function across the different layers. You can have, for example, ReLU in the hidden layer, and you can have Softmax in the output layer. Okay, so now with the understanding of the activation function, based on the output, you get your predicted value, or you get your predicted output. How do you know if the result is correct? Okay, I touched on earlier that you actually have the actual result. So based on the predicted result of your model, you compare with the actual, and then you see whether it is correct or it is not correct. Okay, and you can use an assessment method which is called a loss function or a cost function, basically to measure the difference between the actual and the predicted outcome. Okay, and the measure is used to calculate the error for your model, and actually the objective of training your model is to reduce the error as much as possible, or to get the minimum level of error. Basically, you want your model to predict as high actual results as possible. Okay, and that is the objective. Okay, and that is the objective. Now the question is, what are you going to do if you have a large error, or if you have a high loss function or loss value? Because high loss value indicates that your model is performing bad. You want the values to be minimized. You want the values to be minimized. You want your model to predict correctly. Okay, now remember, when you calculate the cost function, which is the difference, okay, if it is significant, you know that, or if it is high, you know that your model is performing worse, or it's not performing well in predicting the output. What do you have to do? What do you think you have to do if, when you train your model, you realize that the performance is poor? What do you have to do? What do you think you have to do? If you train a model and then you evaluate it on the actual result and you get a poor performance, what do you think you have to do?
I think you can increase your data sets, or you increase the quality of your data set.
Okay, you can increase the number of samples that you have. You can increase the data set. Okay, what else can you do on the model? Yes, you can check the quality of your training data. Yes. What else? Better selection of features. Okay, better selection of features. If you notice, we actually have not talked about extracting features from the input data. And this is because the model learns the features on its own. We don't have to explicitly tell it the features to learn. Okay, and that is one of the good things about neural networks, because they learn based on the amount of data that you have, and that's why they consume, or they require, a large amount of input data. Okay, so I'll keep feature selection or feature engineering at the moment for now. What other approach do you think we can take? to improve the performance of our model.
Or
If we
you can, I think there's a gradient descent, and there's a
say that again,
there's gradient descent,
gradient descent. Okay.
there's reducing overfitting. And there's also that nice trick that you see what sets of fire when making this particular prediction.
Okay.
It also
The
changes the activation function.
okay. I didn't get all of the things that you said, but I think you said gradient descent and also changing the activation function. Okay. Now, yes, you could change the activation function. But if you remember earlier, I said the weights on the link, those are learned while the model is being trained. Now, if the model determines the values of the weight, and based on the weight, the output is determined, and then we compare it with the actual result, and we realize that the results are poor. Shouldn't the model go back and change their weight? Shouldn't we tune the weight so that we get a better performance? Because this are the, in addition to the activation function being a parameter, the weights also are parameters which are determined during training. And depending on the values of the weight, your performances are going to be different. Okay. So what we can do is, after determining or after computing the cost function, and the cost function can be determined depending on the type of problem that you have. So if it's regression, for example, you can apply the mean square error. But if it's a classification problem, you can apply a cross entropy, okay, to give you an idea of the cost function. But in any case, what you want to do is you want to minimize the cost function, okay? Whether it's regression, whether it's classification, you want to minimize the cost function, okay? Now, there is one concept that was actually, I think, instrumental, or one of the most instrumental concepts in neural network, which is depending on the values of the cost function, the model is going to go back. So it will go back and tune the weights. Okay, it will go back and tune the weight until it gets a better performance, or with the objective of getting a better performance, meaning minimizing the cost function. Okay, so if the difference between the prediction and the actual output is significant, you can go back and adjust the weight and the biases. Okay, and this concept is called backpropagation. So what we did earlier, going from the input layer, determining the hidden the values of the neurons in the hidden layer, and then getting the output, that is called a forward propagation. Okay, but the ability of the model after the forward propagation to determine the cost function and to go back and change the weights, okay, that is back propagation. So it goes back from the cost function and determines how to change the weight in order to improve the performance. Okay, so if the weights are changed, a new cost function will be computed. If the cost function is still high, it will go back, change the weights again, compute the output, go back again, change the weight, compute the cost function. This will continue to happen until you have the lowest cost function. Okay, this will continue to happen until you get the lowest cost function. But the question now is, how would the weights be adjusted? Yes, we determine the cost function. The weight needs to be adjusted. How should the weights be adjusted? Should the weights be increased? Should the weights be decreased? What should be the magnitude of the weights as well? Now, in order to do that, you have to apply a such strategy based on the cost function. Basically, it has to be iterative. You have to, you change the weight, you determine the cost function. You change the weight, you determine the cost function. Change the weight, and so on, until you find a cost function that gives you the minimum, and then the weights you will take as your final weights. Okay, the weights you will take as the final weight. Okay, in order to determine the how to change the weight, there's a concept called gradient descent, okay, which is basically the process of trying to find the minimum cost function, or the point at which the cost function is minimum. Okay, very briefly, what the gradient descent determines is, one, it determines the direction and also the size. So how much to change the weight by. How much in terms of the direction? Are we going to go positive or negative? Are we going to go right or left? Okay, and also, how much should we change it by? Okay, how much should we change it by? Okay, so which direction should you take? That is determined. I mean, this involves derivative, but I'm not going to go deep into that. But let's say you start, at some point here. Okay, and the objective is you have different weight values, you have different cost functions. You want to settle somewhere here. You want to determine the weight that gives you the lowest cost function or cost value. Okay, that is the objective. Now, with the gradient descent, we start from a random place, but this is where we want to end up in. So the first thing that we need to determine is, based on the derivative, where do we go? Do we go right, or do we stay on the left? Okay, do we go right, or do we go left? So it determines, the first thing that we need to determine is the direction. So you calculate the derivative of the cost function, and let's say it is negative. Okay, this means that the slope is negative and you are on the left side of the curve. Okay, now if you want to go to the bottom, then you have to go down. Okay, you have to go down to get to the bottom here. Okay, so you go down and then you keep going right. Okay, now what if you are at a point here? Again, you calculate the derivative. The derivative is going to be positive in this case. So you know that you're on the right side. And in order to go to the bottom, you need to go down on the left. Okay, so you keep doing that to determine whether you go left or you go right. Okay, you either go left or you go right. So basically positive or negative. So that's the first thing, to determine the direction. Another parameter that you have to determine is, so based on the direction, you can bounce like this, you can bounce all over the place. Okay, and the cost function, every time you decide, will take you, will take a specific direction, and the process will be repeated until you eventually end up very close to the minimum here. Okay, so this is the direction. That's the first thing that you need to determine. The second thing is not only the direction, am I going right or am I going left, but how much steps should I take, or how much distance should I cover, or how much how far should I travel? Okay, that's what you want to determine. So if you are at this point, okay, you determine the direction you want to go right. Okay, how far right should you go? This is the magnitude of the value. Okay, how you should go. Okay, so that is the second question that you have to find. Okay, beside the direction, am I going left or right? But how much should I go left? How much should I go right? Okay, and this is where the learning state or the learning rate determines the learning speed. Basically, what that means is, how far should you go? If you have a small learning rate, it means that you're going step by step. small step, small step, small step, small step, small step, small step, and so on. Okay. If you have a large learning rate, okay, and depending on the direction that you go, so you might actually go from here, you might shoot there if the step is very wide. Okay, if the step is very wide. Okay, but what you want to do is you want to determine the step that it is not too long of a step, it is not too short of a step. Because if you have a small step, it will take you a very, very long time to get to the bottom. Eventually you get to convergence to the minimum, but it will take you an incredible amount of time. Okay, but if you go a large learning rate, then you just bounce all over the place, and you might not necessarily get to the optimal minimum. Okay, so you might not necessarily get to the bottom here because of the amount of step that you are bouncing. Okay, so the learning rate is a parameter that will determine the speed. If you have a very small learning rate, then it will take you a long time. If you have a very large learning rate, yes, it will not take you a long time, but you might not reach the optimal minimum. Okay, and that is a parameter that you have to tweak based on your training. Okay, so to see the overall process, okay, we understand that backpropagation, how gradient descent applies there, and how the weights are changed. Okay, and for each weight, you're going to get the corresponding cost function, and you have to repeat the process. And this repetition of the process from all of the steps that we have done until now, if you do that one time, so if you repeat one time, it is called one epoch. Okay, so this is another keyword, epoch, which is the number of complete pass that you go through the data set. Okay, and this epoch is also a parameter that you determine. So the number of epochs is also a parameter. If you have a higher number of epoch, it means that this process will go iteratively high number of times, and there is a likelihood that the higher the epoch, the lower the cost function would be. Okay, so the weight or the parameters are adjusted until you have the cost function reaching the ultimate or the optimum. Okay, and you can tell that the cost function has reached its optimum when the value either stops increasing over multiple iterations. So if, let's say, you have 100 epochs, and then after 50 epochs, you realize that the cost function does not decrease further, then that means that actually it has reached its optimum. Okay, so you can stop training at that level. Okay, so this is in short how a neural network learns. So it iterates the learning by continuously adjusting its weight to improve the behavior until it reaches the best result. Okay, and if you think about it, this is how humans learn. Okay, this is how humans learn, basically trial and error. We perform activities, or we do things, and then we learn from it, and we adjust ourselves. We become better. We do things, we learn from it, we become better. We do things, we learn from it, and we become better. And that is the similar process that a neural network takes. Okay, and in order for it to learn, you have to give it a significant amount of data. And that is why when you're conducting a deep learning project, you really are going to have to use a large amount of data. Because if you use a small amount of data, there's another concept of overfitting and underfitting, which results, based on your model. If you have a big model, especially, and you have a small amount of data, your model will learn your data too well that it might not necessarily generalize well when you give it a new sample. Okay, or it might generalize not well on your data, but then it will give you a variant behavior on new set of data. Okay, that's a different set of problem. But for neural network, this is how they work. The very basic to recap, you have input You have input data, you perform linear or weighted sum, and then you apply an activation function. You do that until you get the output. Once you get the output, you compare it with the actual result, compute the cost function. If the performance is poor, then you can apply backpropagation using gradient descent to adjust the weight. Okay. And once the weights are adjusted, the cost function will be computed again, and this process will continue to happen until the cost function is minimum or until the cost function does not significantly decrease or does not change. Okay, and this process continues to happen. And that is why it requires a huge amount of computational resource when it is learned, especially because you might have a deep, significant amount of neurons in the layers. And actually, the difference between artificial neural network and deep neural network is the number of hidden layers and the number of neurons in the hidden layers. Okay, so this is in brief how the neural network works. If you remember, we mentioned convolutional neural network and recurrent neural network. They are basically variations of this architecture. So rather than simply do a linear computation, they might have other computations that they do. For example, in convolutional neural network, they have convolutional filters that they apply on the data, and they are mostly applied to images and videos and those kind of data sets. Okay, so just to recap on the concepts that we have seen, the weights and the biases. We looked at what neurons are and the layers, and you can have any number of layers, hidden layers, and you can have any number of neurons in the hidden layers. But of course, with the understanding that the higher number of layers that you have, the higher number of neurons that you have, the more complex your network is going to be, and the more time it will take to train those networks or that network. We also have seen activation function, which prevents linearity. And we can apply different types of activation functions on different to different layers, and also depending on the problem that we have. We have seen also cost function and how they are obtained, basically by comparing the output of the model and the actual output of the sample. Okay, and depending on what the cost function is, you can go back and change the weight, and the weights are determined, well, the change in weight are determined by the learning rate to determine how large or how small the weights should change. And that process is done iteratively through backpropagation, and the number of times that you go is determined by the number of epochs that you set. Okay, the higher the epochs, the more training or the more iterations it will go, and the higher chances that you're going to arrive at a small cost function. And the gradient descent is how the weights are determined. The values, the change in weights are determined. Okay. For the weight and the bias, these are parameters, and the parameters are decided by the machine during training. So initially, random values are set, but during the training, they are tuned. Okay, during the training, they are tuned. Then the layers, neurons, activation function, learning rate, and the number of epochs, those also are parameters. Okay, those are parameters that you can actually set. So you as the developer of the network, you set the number of layers, you set the number of neurons, you set the activation function, you set the learning rate, and then you set the epochs as well, the number of epochs as well. And these are considered to be hyperparameters. Okay, and these are how the model learns. Okay, it is determined by you, the developer, and you determine it before training. You determine the number of layers, the number of neurons, and the other hyperparameters prior to starting to train. Okay. In terms of the activation function, or the cost function, there are many types of functions that you can apply. Okay, we touched on the mean square error, but there's another one, root mean square error, there's mean absolute error, and so on. Those are all different metrics that you can apply for the cost function. Okay. Philip, how are we doing with time?
I mean, you can continue. Yeah, let's push it small.
Okay, so let's see what we have. Okay, I want to. Okay, I will continue until I come to recall and precision. Okay. Now, remember I said you need to evaluate the performance of your model. And actually, depending on the type of problem that you have, whether it's, in this case, we're simply looking at supervised learning, depending on whether it is regression or classification, there are different metrics that you can derive and different metrics that you can compute to give you an idea of how your model is performing. So the mean square error, so let's start with the regression. The regression, because the output is a continuous value, the metrics for computation and for evaluating the performance of your model is either the mean square error, and in this case, we have the root mean square error, which is basically taking the square root of the mean square error, so the square difference between the observed and the predicted value. That will give you an idea of how your model is performing. And the smaller this value is, the better your model is performing, because this is computing the error. Okay, so the smaller the root mean square error is, the better your model is performing. Okay, there is also another one, which is the mean absolute error, and also there is a coefficient of determination, which is R squared. Some of you might know about. Okay, but in order to compute this, basically the difference between the predicted values and the observed values are taken. Okay, so if you think of, you have different data points, and then you feed a regression line to get the measure of the performance. You basically get the distance between the points to the line. Okay, and this will give you an idea of the fit of the line to the data points. If you have a small error, it means that, so if you have, let's say, you have a line like this, okay, which is closer to the line, you're going to have a lower error. Okay, or your root mean square error or the mean square error will be lower than, say, a model that fits like this. Okay, so the smaller the error, the better your model is performing. Okay, so this is on regression problems. But for a classification problem, and let's stick with the example of the cat and dog. So if your model tells you a sample is a cat, and then the actual result is a cat, then that is a correct prediction. If it is a cat and then the output is a dog, that means it is an incorrect prediction. So there is a form of representation of the performance of that particular model, that particular classification model, and that is called a confusion matrix. This is basically a matrix. Okay, in this case, because we have two classes, we consider one of the classes to be positive, which is cat, and then we consider the other class to be negative. Okay, and then we plot the predicted values, so what the model predicts, as well as the actual. Okay, so what we do is we count how many samples do we know that they are cat, and the model predicted them as cats. Okay, when we have those, that is considered to be true positive. So the sample, the true label of the sample is a cat, and the model predicts it to be a cat. That is true positive. Okay, and then we have a count of it. Okay, out of the number of samples that we have, then we put a number. Okay, let's say X. Then we also see how many outputs are a dog and how many the label predicted as a dog. Okay, if the output is a dog, the prediction is a dog, that is true prediction. And in this case, because dog is a negative class, then we say it is true negative. Okay, we say this is Y. Then we might have a case where the actual label is positive, but our model predicts it to be negative. And that is called a false negative, which means the model predicts it to be negative while it is positive. Okay, so the label is a dog, but the model says, or the label is a cat, the model says it is a dog. That is false negative, and that is considered otherwise called a type 2 error. And then we have the other case where the actual label might be a dog, and then the model predicts it to be a cat. Okay, that will be false positive because the model predicts it to be positive, but the actual label is negative. So that's false positive. Okay, so we build a matrix like this, let's say A and B. We build a matrix like this that tells us true positive, true negative, false positive, and false negative. Okay, and these are the actual counts. So if you have, for example, you evaluate your model with 10 samples or 100 samples. Okay, let's say you have 50 dog and 50 cats. Okay, you count how many dogs, how many cats were actually predicted as cats. You put them in the first cell. How many dogs were predicted as dog? You put them in the last cell. How many cats were predicted as dog? You put their number. And how many dogs were predicted as cat? You put their number as well. So this will give you a matrix of numbers. Okay, let's say for the sake of example, you might have 30, 20 here, maybe 20 here, and then here would be, if this is 20, then this will be 30. Okay, so you have this, which is called a confusion matrix. And if you are confused, that means the naming is appropriate. Okay, but the idea here is you count how many actual labels were predicted correctly, how many were predicted incorrectly. Okay, and you put it in a matrix like this. This is the actual count. Okay, the actual count. So the total number of the samples has to correspond to the total number of samples that you used. And then you have to derive, so to give you something like this, and then you have to derive what we call performance metrics. Okay, performance metrics, which are the metrics that you're going to use to see how your model is performing. And two of the metrics here are recall and precision. Okay, recall and precision. Recall, this refers to all positive cases and looks at how many were predicted correctly. Basically, out of the total, out of all of the positive cases, how many were predicted correctly. And the equation is you take the number of true positive, you divide by the number of true positive plus false negative. So this is out of all of the positive cases. So out of all of the positive cases, how many were predicted correctly? That is what recall tells you. And then precision tells you out of all of the cases that were predicted as positive by the model, how many were actually positive? So out of all of the prediction of the model, how many were predicted correctly? Okay, that gives you the precision. Okay, so recall tells you out of all of the positive cases, how many did the model get correct? The precision tells you out of all of the positive cases, out of all of the positive prediction that the model made, how many did the model get correct? Okay, and you can get the recall based on the number of classes that you have. So in this case, with this example of a cat and dog, you're going to have a recall for cat, you're going to have a recall for dog. You're also going to have a precision for cat and precision for dog. So you're going to have 4 values. Okay, 2 precision and 2 recalls. Okay, and there are other metrics that you can compute. For example, you can compute the accuracy. Basically, how many total predictions were correct. So in that case, you take true positive plus false positive plus true negative over all, basically. Okay, over all. So basically, you take the diagonal, divide by everything. That will give you the overall accuracy. Now, one of the reasons that the recall and the precision are preferred over the accuracy is that you might have a data set that is highly skewed. So you might have a highly imbalanced data. So let's say, for example, you have 100 samples, but then 90 of them are cats, and then only 10 are dog. If your model predicts everything to be a cat, then your model will be 90% accurate. But then none of the dogs were predicted correctly. Okay, and this is just an example to show you how the recall and the precisions are computed. Okay, so let's say you have a 100 fish in a lake. Okay, and then you caught 80 fish and 80 rocks. What would be the recall? In this case, the recall would be 80% and the precision would be 50%. You might ask, how would you get 80? How did you get 80% or how did you get 50%? Okay, so the recall is out of 100, okay, out of 100 fishes, 80 of them were caught. That's why 80%. Okay, that's why 80%. And the precision, it's, okay, how many fishes were caught? 80 were caught out of the total catches. So this is 80 over 160. 80 plus 80, 160. You take 80 fishes, that will give you 50%. So that's how the precision is taken. The recall, out of all fishes, how many were caught? Precision, out of everything that was caught, how many were fish? That's what the precision tells you. So you see that it gives you sort of different views of the performance of the model. Okay, and this is also another example that will give you the measures of the recall and the precision. Okay, so whenever you build a classification model, well, you need to have the confusion metrics as well as you need to have the performance measures, and precision and recall are one of the most important, because even your data set is imbalanced, it will actually tell you per label how the model is performing. Okay, per model, how the model is performing. Okay, and just to summarize, based on the confusion metrics, you can derive the recall, you can derive the precision, you can derive the accuracy, and there are other measures that you can derive based on the confusion metrics. Okay, and I hope this gives you a bit of clarity. One thing that I want to emphasize before we go is there's actually a trade-off between recall and precision. Okay, depending on your use case, of course, and depending on what you want to optimize. For example, if it is if your goal is to catch as many spam emails as possible, then you might prioritize recall. So out of the different spams that will come, you need to get as many of them correct. Okay, but in contrast, if your goal is to catch the messages that are definitely spam without blocking other emails, then you might prioritize precision. So you might prioritize, okay, definitely the ones that are caught, I want them to be definite spam. Okay, So there's always a trade-off, and that trade-off, of course, you have to look at the context and the problem that you have in order to determine which direction you want to sort of trade towards. Okay. Okay. So I'm going to stop here, and I hope you have at least a general understanding of a neural network, how it works, the output of it, and what happens in terms of tuning it, as well as how you can evaluate the regression model as well as a classification model. And these are fundamental to understand. Okay. If you encounter any supervised problem or any regression or classification problem, you will need to understand, you need to express the understanding of how the models are built, or generally how they work, the differences between them, and also how the models are evaluated, because the evaluation is not the same. The evaluation is not the same, simply because the outputs are different. In classification, you have categorical labels. In regression, you have numeric output. So you cannot evaluate them in the same way. And it's very important to understand the different ways in which they are evaluated. Okay. And I'm going to stop here and take any questions that you might have at this point.
Thank you very much, Naser. Please, you have questions, you can just unmute yourself and ask, or drop them in the chat. So somebody was asking, how do I get the recording? So I pasted the YouTube channel on our chats. After that, you will find lesson 1, day 2 on the YouTube channel. Please subscribe to the channel so you'll be notified about as we are dropping this series. All right. You can also join the WhatsApp group if you want to learn with others and see what they're doing, follow their progress. You can join the WhatsApp group. Yeah, so thank you very much. I think let me stop the. So do anyone has any question at this point before we close up? So hopefully our next lesson will be on next week, Monday. If the date will change, we'll get an email, but hopefully it should be next week, Monday. Thank you very much for this great introduction. All right. Awesome. All right. Thank you very much, everyone.
All right. Thank you very much, everyone. Have a good rest of the
Thank
day.
you.
Bye-bye.